Greetings, math friends. We are going to look at a number of problems which have some component of the greatest common factor that are involved in them. When you learn about fractions and adding fractions, you know you have to have a common denominator when you add. So I need some denominator that I can share in common with what I'm adding so that I can properly add. And you're usually taught to look for the least common multiple when you do this. And the idea is you want to set yourself up in a way that you don't, in the end, have to make a reduction of your fraction. So for a case of 9 and 27, I can multiply 9 by 27. So 27 and 9 have something in common. I can multiply one by a number to get the other. So 9 times 3 is 27. I won't have to adjust this fraction at all to be able to add them, and I would simply use a factor of 3 here to convert this to be 27 and 6. And then I can add the 6 and the 4 to get 10 27s. And I know since this is the least common multiple, there's no factor in common here that I would reduce by. So this is my final answer. Another approach to look at this is to say, what is the greatest common factor between 9 and 27? 9 goes into 9 one time. 9 goes into 27 3 times. So this is 9 times 1 and times 3. So when we look at factors, factors are things that multiply together to give you a number. The biggest number that we can multiply to get both of these numbers is 9 itself. 9 times 1 gives me the 9. 9 times 3 gives me the 27. So if you're struggling to find a number that is in common with the idea of looking at the least common multiple, another approach you could think about this as is, what is the greatest common factor? Since I see that 9 is the greatest common factor, and I can get from 9 to 27 by multiplying by 3, then really I've found that the least common multiple, the product that I get from multiplying the factors, is that 27. So these are kind of related to each other. Multiples are the result of multiplying factors. So it is kind of hidden in here. When you do reductions, if you have to reduce a fraction, if you reduce by the greatest common factor, you have a single reduction. Otherwise, you could go through a series of steps of reducing until you get it down to lowest terms. So they do kind of work hand in hand, though they're not the same thing. They have some similar ways to think about them. They are interrelated in factors give you a result of multiples. I hope that introduction was clear enough to demonstrate some of this interconnectivity. I want to look at this story problem. A school is making spirit bags for a fundraiser. They have 48 stickers and 32 pencils. They want to make the greatest number of identical bags possible with no items left over. How many bags can they make, and how many of each item will be in each bag? So looking at this, we have 48 stickers, and we have 32 pencils. The sum of these is not important. The product of these is not important. What it is we need to take each of these and divide it by the same number. And those quotients are going to represent the number of each of these things in each bag. So what number can we divide both of these by to get a natural number solution? We're not going to cut stickers in half to put them in a bag. So we want a factor that we can pull out of each of these. And we want it to be the largest factor that we can pull out of each of these so that we get these nice natural number solutions. If it would help, you could write this like a ratio. And that's kind of the question. What is the ratio reduced that is going to be stickers to pencils or pencils to stickers in each spirit bag? So in this case, we have pencils to stickers. We can reduce ratios just like we do fractions, and sometimes you see in a ratio lesson that they do put ratios like they are fractions. So you can think about reducing a fraction. And this goes back to my previous discussion about how common multiples and common factors kind of have this interplay within the study of fractions. I can take out a common factor that's not the greatest common factor. I can divide each of these by 2 because I see that they're both even numbers. This is not the greatest common factor, which means I'm going to have to make a reduction after this. If I divide each by 2, then I'm going to have 16 and 24 here. Okay, so I just make a note that I divided by 2 there. If you know the greatest common factor, you can immediately divide each of these by a single number and get the total reduced fraction, which is really, in this case, the reduced ratio that we need. Another approach that we can use, we can simply write out in the numerator here all of the factors that multiply together to give me 32. And you can write 2 times 16, 3 times 14, 4 times 8. And we have this list of factors here. And all of these will give me 32, which is the multiple. We do the same thing for the denominator. And as we look at the numerator and denominator, we're going to look for the largest number here. Each of these is a factor. So the largest of these factors is the greatest common factor. So in this case, we have 16 is the greatest common factor. If we divide the numerator and the denominator by 16, we will have the reduced fraction. In this case, we will have the reduced ratio that we want. 16 goes into 32 2 times. And 16 goes into 48 3 times. This is the ratio of pencils to stickers that we want. So this is the ratio per bag. And the greatest common factor is really the answer to the question, how many spirit bags will we have when we take this amount of materials and divide them into these bags with no remainders and not cutting stickers in half. So this is 16 spirit bags. So this shows a very real-world type of problem that students may encounter in a school fundraiser. We have this set of materials. We want to have a fundraiser, sell these bags. The next question that students would have to come up with to make this really robust is to have this as an economic question. For our second problem, we are going to look at one that has a bit of geometry to it. An interior designer is tiling a rectangle floor that is 120 inches wide and 144 inches long. The client wants the floor to be covered in the largest possible square tile so that no tiles have to be cut, so we're looking at no waste essentially. What should the length of each square tile be? So for this to be square, I need the same distance on this side and this side of the square to be a square, but we have a rectangular floor space. So as we look at 144 and 120, we need a common factor of each of those to be able to break out into square pieces. So with this problem, we could look at it as a ratio again or a fraction and find common factors there. We can see that 2 is certainly going to divide this, but 2's probably not big enough. So we could ask questions about larger numbers. 144 is a square number itself, so we know that 12 will definitely divide this. Will 12 divide this? Well, you can see that we have this 12 leading this. 10 times 12 will divide this. So already we've got a nice starting point. We need to figure out, is there a number larger than 12 that will be in common here? Because again, we are going for the greatest common factor here. So we could try doubling 12 or doing triple 12, some kind of multiple of 12. Doubling 12 would be 24, and we could ask, does 24 go into these numbers? Dividing 24 into 120 gives us 5. Dividing 24 into 144 gives us 6. If we try to up this to 36 and divide 36 into 120, we see that that does not divide evenly. We get a decimal expansion on that one. We end up with 3 1/3. 24 turns out to be the greatest factor in common that we have here. So if we have a 24 by 24 inch tile, we should be able to cover this entire floor. We will need 5 tiles in this direction and 6 tiles in this direction. The third problem that we're going to look at is solving for x using the greatest common factor, and we're given 36x squared equals negative 6x. Some of you might recognize that this is a quadratic piece on the left-hand side, so we could use Hartrau's formula. But since we're given specific directions to use the greatest common factor, that's the technique that we need to use to solve this, and that really does come out very nicely. The first thing that I'm going to do is move both of these terms to the left-hand side. So I'm just going to add 6x to both sides. And that leaves it equal to 0 there. Again, we have this nice quadratic here. But now, using the greatest common factor, we're going to look at what is in common between the two pieces here. We see that 6 will divide 36 and 6, and also there is an x in both. So the greatest common factor ends up being 6x. If we take 6x out of 36x squared, we end up with 6x. Over on this side, we're going to end up with 1. Since these are equal to 0, by the zero product property, it means that either this or this has to be 0 for the product to be 0. So we're going to create two cases. In case 1, we're going to put this piece equal to 0. And in case 2, we're going to put this case equal to 0. And now we're just going to do the algebra. We're going to solve each of these cases for x. Dividing on both sides by 6, we're going to get x is equal to 0. And that's really easy to see in the original. If I plug in 0 here, the whole left-hand side goes to 0. If I plug in 0 here, the whole right-hand side goes to 0. Over here, I'm going to subtract 1 and then divide by x. So I get negative 1/6 over here. So I have 0 or negative 1/6 is going to be solutions for this by using the greatest common factor as a part of my solving technique. For the next problem, we are going to factor a trinomial using the technique of greatest common factor. The first thing that we want to do is we want to find two numbers whose product is this and whose sum is this. Looking at the 8, we can look at negative 4 times 2. This will give us the negative 8. If we add these together, it will give me the negative 2. So these are the two numbers that I'm looking for. I have changed from having a trinomial to having an expression that has 4 terms in it, but these 2 terms in the center are like terms, so they would simplify to this term. So I haven't changed the value of this, I've just changed the look. Now that we have this, by the associative property, we are going to associate the first 2 terms and the last 2 terms and use the greatest common factor here and pull out that greatest common factor. The first greatest common factor is just x, and the second greatest common factor is 2. As we look at this, we see that now we have a product, a sum, and a product. And in each of these products, we also have a common factor. So we're going to pull that common factor out. And as I look at this, if I divide x minus 4 by x minus 4, I have 1. 1 times x is just x. And over here, likewise, if I divide by x minus 4, I end up with 1. 1 times 2 is 2. So these are the 2 factors of this trinomial, and we've used the greatest common factor not once, but twice to find this solution.